The first assignment for Comp 3430 in the summer of 2025 is going to have you building some code or writing some code that will implement reading a file system. The file system that I'm asking you to read in this assignment is EXFAT. And the way that you're going to be building this implementation is to implement an interface that looks a little bit like the POSIX interface that we've been using in class to work with files. So I'm going to start by taking a quick look at some of the general submission requirements. I won't spend a lot of time dwelling on this in other assignments when I'm talking about them in class, but I do want to take the moment to talk about them now because they will apply to all assignments in the course. The first thing is that all code that you submit in this course must compile and run on Aviary. I'm requiring this because Aviary is a consistent and common environment for all students in the course, and it's also a consistent environment for you and your grading team when they're assessing your work. Having it be the same for everybody here makes sure that we don't have to worry about things like it works on your machine, but it doesn't work on the grader's machine. I do encourage you to have your own Linux environment set up on your own laptop to do local development because it can be kind of painful sometimes, especially when you're off campus and having to connect with the VPN. But I urge you to make sure that your code compiles and runs on Aviary somewhat frequently as you're going through and working on stuff on your own laptop. All code that you submit must run to successful completion. And so what I mean by that is, at least in the case of this assignment, the code that I've provided for you, the sample code that I've provided that uses the interface that you're implementing should complete. In all cases, it's code that should complete. And any reason that the code stops prematurely, so for example, there's no obvious output from the program, there's a segmentation fault, core dumped, or there's a bus error, then this is going to be something that's considered to be code that doesn't run to successful completion. If the code compiles and it starts to work, that doesn't necessarily mean that you're going to get the hard 0 on the assignment. Instead, what the way that this is going to work is that if code does not complete successfully, the level of rubric that your submission is able to achieve is capped at about 50% of that specific rubric. So I'll look at the assessment of this assignment a little bit later, but I've tried to make the assessment for the assignment be tied to the behavior that you're implementing in your code. And so when the grader is assessing that specific behavior, if it doesn't run to successful completion, then you're going to be capped at most at 50% of the total score. The final part is that all code must compile, and this is a hard requirement. So it has to compile on Aviary and it has to compile. If code is submitted that does not compile, the graders are not going to evaluate that submission at all. There are some exceptions to this, and they're explicitly noted in rubrics, but this assignment is not one of those cases. Any code that gets submitted as an assignment, as part of an assignment for this course, is going to be compared against all other submissions in this term, and it's also going to be compared against other submissions in previous terms. So the assignment itself, now onto the good stuff, is I want you to implement an interface. The interface that I want you to implement looks a lot like the POSIX interface. POSIX here, the POSIX interface for I/O, to me is functions like open and read, seek, close, and to be able to do things like get directory entries. So to be able to list the contents of a directory. You are going to be doing this. You're going to be implementing an interface that looks a lot like this POSIX interface, and your implementation of this is going to be specifically for EXFAT formatted file systems. The way that your implementation is going to be assessed is that you are going to be using some sample code that I've provided for you to that implements GNU core utilities. So this is things like ls and cat, some basic programs that will use this interface. The EXFAT documentation, and I've opened this a few times in class. and I'll probably open it more in class, and I would suggest that you open it frequently, is the exFAT file system specification. This is the universal source of truth for everything that is exFAT. We unfortunately are, fortunately or unfortunately, I guess, we are fortunately or unfortunately not going to be working with hard drives. That's a little bit outside the scope of this course, but instead we're working with binary files. The binary files themselves are volumes, so this is a volume, and each of these volumes are going to contain an exFAT file system. All the volumes are in a repository on GitLab, which I've got open here, and all of these different volumes are volumes that will try to assess different kinds of behavior in your implementation of exFAT. The volumes are all these files that end with the suffix .img, and each of them are going to, like I say, test different things about your implementation. The README file here describes in detail what it is that you should be trying to assess with the different volumes that are here, and it describes briefly how they've been created. At the very end of this README file, I describe how you can go about making more volumes if you want. This is something that you have to use an actual proper Linux environment for if you want to be able to do that. The interface that I want you to implement is also in a repository on GitLab, and the interface that I'm looking for you to implement is this one, nqpio.h, not quite POSIX io.h. The functions that I'm looking for you to implement here are mount, and what mount is going to do is effectively open the volume. You'll be passing the volume's file name as a string here. And then it's going to do some basic file system checks on the main boot sector of this volume. The things that I want you to check are in the rubrics, and I will go to the rubrics a little bit later to give you an idea of what's being expected here, but you don't have to be doing a comprehensive file system check on this, just some basic checks. The unmount function can effectively do nothing except for make sure that there is a previously mounted file system. This volume label function is one that's going to be asking for a property from the file system or from the volume that's describing its label. And so this is a human readable string that can be added or put onto a file system, a volume, once it's created. And this is going to be used for things like printing out what the volume's label is. NQP open and NQP close, these are functions that are going to be working with the actual files in the volume itself. The paths that get passed to NQP open will always be absolute paths. So we're always going to be passing something like / file name or / directory name and then a file name. It's always going to be a complete file name, but NQP open can be a file or a directory that's in the file system. This is going to be where you're implementing, going through the process of building up entry sets for files to be able to find the thing that's being asked for here. And this is going to involve a little bit of string processing in the form of tokenizing stuff. The close function is going to basically take anything that has been opened and mark it as though it's closed. It doesn't really have to do very much here. The open function should return an integer that is a file descriptor, and the file descriptor that you're going to be returning here is your own internal file descriptor. So this is going to be something that you're building as part of this implementation with every file that gets opened will have some metadata attached to it, like what your current offset is in the file. So I want this to behave a lot like what the POSIX interface looks like. So as you're opening something, you should be adding an entry to your open file table for this thing, and you're returning the index into that open file table as that integer, or however you choose to implement this open file table. The read function here is going to behave like read. And so it looks the same as read does in terms of it expects a file descriptor, it expects a buffer, and it expects a number of bytes that you want to be copied into that buffer. This is where you're going to be going through the process of finding the clusters for specific files. So these are actual files. This is not directories, this is files. And the idea is that you're going to be putting into this buffer the contents of the cluster that you read for that file. This will involve going through the process of building up cluster chains where it's appropriate, and making sure that you're able to span across clusters when you're trying to read data from the cluster heap for the file that you're working with. The getDents function is one that's going to be used for reading the contents of directories as opposed to files. The way that we're going to be reading the contents of directories here is that we're using this NQP-dir-ent structure. I'm going to scroll up here a little bit. The NQP-dir-ent structure here is this one. The idea is that you're going to be taking the directory entry sets that you get from exFAT. So that's those three things: the file directory entry, the stream extension directory entry, and the file names directory entries if there are more than one. And you're going to be translating that into an instance of this type, which is NQP-dir-ent. The inode number, there are no inodes in exFAT. You may have read about this when you're looking at BSFS, but there are no inodes in exFAT. This is a value that you can populate using the first cluster that you get from the stream extension, the first cluster number that you get from the stream extension. The name length and the name are things that you should be getting from the stream extension. The file size is something that you should be getting from the stream extension. And the type is something that you're translating from the file directory entry. And the type can have two possible values. It's a regular file or it's a directory. The last functions that is in this interface is lseek. And lseek is going to behave similar to the way that lseek does in the regular POSIX interface. So we're passing file descriptor, an offset, and then this whence value. Whence is going to be one of those three things: seek set, seek cur, or seek end. And the idea here is that you're going to be making changes to the offset that you have in the open file table for this file descriptor. The template directory itself also comes with two other files. This one is called nqp-exfattypes.h, and this is where I have gone through the process of building up a bunch of structures in C that represent all of the different data structures that you'd need to be working with in the exFAT file system. So the first one here is the main boot record itself, and it's the 512 bytes that represent the main boot record. And it has things like where the cluster heap offset is, and where the FAT offset is right here. So these are the values that you're going to be using. This is the file system's metadata itself. And then beneath that, there's a whole series of directory entries. So there's file directory entry, the stream extension directory entry, the file name directory entry. There are other directory entry types here, like an allocation bitmap. This is an allocation structure in exFAT. The volume label, this is what you're going to be using to get the volume label function implemented. And then there's a generic directory entry type. The generic directory entry type here consists of a single byte. So the first byte of a directory entry is always the entry type, and this value then tells you which of these entries in the union you should be using to decode the rest of the data that you've read in. So the data that we have here is going to be one of these five different types of directory entries. And the value that you can have in the entry type field is going to be from one of these things. You can figure these values out from the exFAT documentation, but it's a little difficult to do it. And so it's here. It's something that you can use. There's some other exFAT specific definitions, like the number of characters or symbols that you can have per file name directory entry is 15, and the number of bytes in each FAT entry is 4 here. The last part of this template folder that is something that you're going to need to work with is this nqp-exfat.c file. The first thing you'll see here is this function that's called Unicode to ASCII. Everything that's in the exFAT file system is Unicode, so it's 16-bit characters, but it's possible to work with these in C, but it's really painful, and so it's easier to just convert them from Unicode to ASCII. This is a function that you can use to do that. So it takes as input the uint16t type that you'd be getting from the directory entry for file name and the number of characters that are in that, and then it returns a regular ASCII character pointer string that it's your responsibility to free afterwards. The other part of this file is just a bunch of functions that don't do anything yet. All they do is cast to void the arguments that they are passed. This is suppressing warnings in the C compiler so that our code compiles when we compile it, but your job now is to implement all of these functions in this file. You are more than welcome to add new functions to this file. You're more than welcome to make changes. You must make changes to this file. You're more than welcome to make changes to this file, nqp-exfattypes.h, if you want. You are also more than welcome to add your own header files if you want. The only thing that you're not allowed to change is this file. You are not permitted to change this interface because this interface is the one that I'm expecting when I'm writing code against your code. The things that I'm going to be doing with your code are things like this cat program. This cat program uses this interface to read data from a file system. There are some examples of how the cat program works or how it should be used in the README for the assignment template itself. So I'm going to scroll down here just a little bit, and it shows that like something like this is how you should expect to run this program. Some implementation notes alongside what we've got here is, like I said, there's a function that you can use to translate between Unicode and regular ASCII. For the NQP-Durant type, you can use the first cluster number as this inode number. I would strongly advise you to make functions that will help you quickly convert between sectors and clusters and bytes. Keeping track of what the current unit size is for the different parts of the system that you're working with. So for example, everything in the main boot region is measured as an offset in sectors. And then once you get to the cluster heap itself, everything there is measured in clusters. The other thing that I'd recommend that you do, and again, this is quite frustrating, is that all of the cluster numbers are off by 2 in terms of their actual index. This is a 2-based array, and it drives me crazy to see this every time I see it, but anytime that you're calculating an offset into the cluster heap, you're going to have to make sure that you're doing this off by 2 arithmetic. So here's an example. If you wanted to get to cluster number 5, then you'd have to go to cluster to an offset of 3 clusters into the cluster heap itself. The directory entry sets themselves here are described. You have to have an entry set for everything, and it's possible that the directory entries here could span non-contiguous clusters in the cluster heap. So in the example that we did in class, we had a pretty contrived example of the first cluster of root directory and the next cluster of the root directory were right next to each other. But in practice, that's not actually going to happen. The first cluster of the root directory is going to be filled with possibly a partial entry set. And the idea then is that once you've read this partial entry set, and part of what I was doing when I was going through the example of going back to the FAT here is, regardless of whether it's the next one or not, you should go back to the FAT to find out where the next cluster in this chain is, so that when you've read the initial part of this entry set, you know that you should be going to cluster number 4 instead of looking at this next contiguous cluster. In terms of assessment, the total number of points that are available for this assignment is 30, and the graders are going to have some privileges and latitude to make changes to the score that are assigned to each of these different functions and behaviors based on the code quality. So like if you're not if your code is a bit of a mess, then they're going to have the option to remove some points, regardless of the level that you've achieved in terms of the behavior that we're assessing. So the mount function here, what we're looking for is some specific parts of the file system to be checked. So I don't want you to go through and comprehensively check everything in the main boot sector. There are only certain fields that I care for you to look at. The boot signature field is one of them. And then the other 3 are the file system name. The file system name must be exfat space. The must be 0 field, I think, is 53 total zeros. And the first cluster of root directory, in the exfat specification, there's a specific set of valid values for the first cluster of the root directory, and you must check that. The open function, what I'm looking for here is going to be kind of a sequence of like increasing complexity. So at the very beginning, I'm looking for you to have some basic implementation of being able to find a file that's in the root directory by name. So being able to respond positively and say that there's a file descriptor here and I found that thing. To move to the next level, then I want you to be able to find a file in a subdirectory. To move to the next level, I want you to be able to find a file that's in the root directory where the directory entry sets are not in one single cluster. So kind of like that example diagram above here that shows where the root directory may have non-contiguous clusters. They're not physically right next to each other. And then the last part here is doing that, being able to call open multiple times. So this is where we're getting to an open file table. So for everything else up to here, you don't necessarily have to have an open file table, but to get to this point, you must have an open file table. For read, what I'm looking for is something similar. So I want you to be able to read the contents of a file when the file is contained within a single cluster and the request for read is less than the size of cluster. This then grows to being something that's contiguous clusters, but bigger than the cluster size for the read request. This then is now going to be non-contiguous. So you have to build a cluster chain for this file, or you have to be able to go back to the FAT to find the next cluster for this thing. And then finally for NQP read, the last part is you have to have an open file table. And this is where we're going to be able to want to be able to do interleaving of reads. So I'm going to read from file A and then read file B and then read file A and then read more from file B. The directory entries part is kind of similar. So we're starting at, let's build up the directory entry set for the root directory, and then kind of going along to building up directory entry sets for things that are not within single clusters, for long file names, and being able to find directory entries that span multiple clusters. And finally, the lseek part is going to be some basic implementation of lseek. So being able to do absolute offsets and being able to do offsets relative to the end of the file and relative to the current location. The very last part here is some instructions about how to submit your code, and we're submitting things with Handin on Aviary. If you don't remember how to do that, you can find more information about how to use Handin by looking at the manual page for Handin or by looking at this chapter in the Introduction to Tools and Techniques textbook that I provided as a link for you here. The main thing that I don't want you to include is disk images. You're not going to lose any points if you do. I'm just trying to save a little bit of disk space here. So that's a pretty high-level overview of the assignment. In class on Monday, what we're going to do is have some open time for questions about the assignment.